Okay, welcome back to part 2. Now I think we should just dive straight into it and get into quite a few examples of a very basic implementation of a file system. So the name of this file system that we're going to be creating together basically is going to be called the very simple file system. So in this section, we're going to introduce a simple file system implementation, and we're going to jokingly call this the very simple file system. And this still represents a simplified version of what like a typical Unix file system would be. And it will serve to introduce some of the basics on disk structures. Okay, what type of on-disk structures are utilized, as well as access methods and various policies that you'll find in many like file systems today. So the file system is pure software, right? There's no hardware to it. It's like a logical layer. And unlike our development of a CPU and memory virtualization, we will not be adding any hardware features to make some aspect of the file system work better. So what do I mean by this? Well, you remember when we had like dual mode operation in our CPU? We added that like mode bit in the CPU to help us identify, is this a kernel mode or is this a user mode? So there is no additional hardware like registers or anything like that which is included in file systems to make them operate faster. The example for memory would have been our like cache or that buffer that would store like the frequently loaded pages. Now there is a great deal of flexibility we have when building a file system, and as a result of that many different ones have been built. But they generally have two main aspects. Now the first is the data structure of a file system, and in other words, like I said already, it is what types of on-disk structures are utilized by the file system to organize its data and metadata. Now the first file systems we'll see employ very simple structures like arrays of blocks or other objects like that, whereas more sophisticated file systems use tree-based structures. However, we're only going to be looking at like the array of blocks idea. Now, the second aspect of a file system is its access methods. How does it map the calls made by a process, such as open, read, as well as write? How does it map these calls onto its data structures? So how does it use these calls to actually access the data? And which structures are read during the execution of a particular function call? Which structures are read during an execution of a particular system call? Which are written? How efficiently are all these steps performed? These are all the questions that need to be solved in this in this access methods aspect. Okay, so let's start with our data structures. So let's develop the overall on-disk organization of these data structures for this very simple file system. And this is going to be quite a long walkthrough example of how this aspect is implemented. So hopefully you'll understand and we can go through it slowly together. Now the first thing we'll need to do is divide the disk into blocks. In this simple example, we're going to say that there's just one size of blocks, so there's only one set size of blocks, and that is going to be 4 kilobytes. So each block is of size 4 kilobytes. So our view, therefore, of the disk partition will look something like what we have here. And we're going to be building our file system as a simple series of blocks, with each block being of size 4 kilobytes. The blocks are addressed from like 0 to n-1. And this is in our partition size of n, n number of 4K blocks. And we assume we have a really small disk, so just like 64 blocks. So here you can see we have 64 blocks, and each of them is size 4 kilobytes. So 0 to 63, obviously that's 64, and each of these is of size 4 kilobytes. So then let us now think about what we need to store in these blocks to build a file system. So of course, of course, the first thing that comes to mind is the actual user data, right? In fact, most of the space in a file system is, and for obvious reasons, it should be made up of user data. Now, we call the region of the disk we use for user data as the data region. And you can see all the blocks that we're using for the data region have now been labeled with D. So we're going to, in this example, once again, reserve a fixed portion of the disks for these blocks. And that's going to be the last 56 of our 64 blocks. So the last 56 blocks are our data region. Now, as we learned about, the file system has to track information about each file, right? And that was utilized through those inode numbers, right? The inode numbers would uniquely identify the files. Now, this information is a key piece of our metadata, or the data that describes our data. And it tracks things like which data blocks comprise a file, so which data block has the specific file that we want, the size of the file, its owner, the access rights, modified times, etc. And to store this information, file systems usually have a structure called the inode. So this is an inode block, okay? So like the inode number referred to a specific file, well, we're going to have an inode block. To accommodate these inodes, we'll have to reserve some space on the disk for them as well. So let's call this partition, or this portion of the disk, the inode table, okay? And this simply stores an array of our on-disk inodes. So all the inodes that are currently stored on disk, in other words, all the files that are currently stored on disk and their inodes, will be held in this array. So the values themselves, right, the integer value. So our on-disk image now looks like what you can see over here. And we're going to assume that we use 5 of our 64 blocks for the inodes. And that is denoted as I over here. So this is going to be our inode table with containing 5 inode blocks. We should also note here that inodes are typically not that big. For example, there are like 128 or 256 bytes. And for this example, we're going to assume that there's 256 bytes per inode. So that means if we do some quick maths, that a 4 kilobyte block can hold 16 inodes, right? Just by simply doing the division there. And our file system, therefore, contains 80 total inodes. And then that's, again, just some simple multiplication to get that. Now, in our simple example here, or the simple file system, it is built on a very tiny 64 block partition. That's tiny compared to like a real world example. Now, this obviously represents the number of files we can have in our file system. However, you can simply note that if we did this on a larger disk, obviously we could allocate a larger inode table and thus accommodate more files. Now, one primary component that is still needed, as you might have guessed, is some way of tracking whether the inodes or the data blocks are actually free or allocated. And such allocation structures are thus a requisite in any file system. Now, many use a free list, and like this is like the free list that we've discussed earlier. And this free list obviously points to the first free block, which then points to the next free block, and so on. We'll instead choose to use a simple but popular structure known as a bitmap. Now, we'll utilize one bitmap for the data region to indicate which data blocks are free and which are not free, and one bitmap to represent which inodes are free and which inodes are not free. Now, a bitmap is a simple data structure where each bit is used to indicate whether the corresponding object or block is free. So 0 indicates free, or in use will be indicated by 1. And therefore, our new on-disk layout will basically have this ID component here. Okay, so moving on from here, we've now allocated a lot of information in this first region, or these first 8 blocks. And it's basically our inode table as well as some metadata blocks which keep track of which blocks are in use. Now you might have noticed that there was that one little block free. Well, we reserve this for what is called the super block, and that is denoted by S. And the super block contains information about this particular file system. And it includes, for example, like we've been talking about already, how many inodes and data blocks are in the file system. So 80 inodes, 56 blocks, data blocks in this example, and where the inode table actually begins. So our inode table begins at block 3. So that information will also be stored in the super block. It will likely also include like a magic number of some kind to identify the file system type, but that's not super necessary to know. And therefore, when mounting a file system, so when actually mounting the file system, the operating system will read the super block first. So it will read this element here first to initialize the various parameters, and then attach the volume to the file system tree. So when files within the volume are accessed, the system will also therefore know exactly where to look for the needed on-disk structures. Okay, because if you don't know where the inode table starts, well, how can you actually access it? If you don't know where the data region starts, or how many data blocks there are, or how can you use any of that information? So obviously this needs to be accessed first in order to understand the structure of our file system. Okay, so let us dig a little bit deeper, or dive a little bit deeper into this inode. Now, it's one of the most important on-disk structures, and virtually all file systems have a structure similar to this. Now, the name inode is short for index node, and this was historically because they used arrays and indexing and stuff like that, so it was called index node. And each inode is implicitly referred to by a number, and this is called the I number, okay? And this is that number that we talked about earlier, which was that low-level name of a file. Cool. So we're going to try see if we can get the location based on the inode number. And you should be able to directly calculate where on the disk the corresponding inode is located, okay, based on the I number. So for this example where we have an inode of 32, we have to assume a few things firstly. So we're going to take this table below here, and this table is basically like a zoomed in version of what I was demonstrating here, but we're only looking at the first 8 blocks, right? We're not looking at the data region, okay? So assuming you're using this table here, there's a few things to note that are important. For example, take the inode table, and it is of size, it's of size 20 kilobytes. 5 4-kilobyte blocks, right? And remember, originally we said that all our blocks are size 4 kilobytes, and you can see that 5 times 4 is 20. And it is therefore consisting of 80 inodes, and that's basically assuming that's 256 bytes per inode number, and we got that from the previous couple slides, right, when we were talking here. Okay, another way you can get it is, well, through a simple division, 20 kilobytes divided by 256, how much does that give you? It should be 80. Let me just check quickly. Yep, that's exactly what it is. So then we further assume that the inode region starts at 12 kilobytes. Okay, we're going to assume that the inode table starts here at 12 kilobytes. So this block here is 12 kilobytes. Okay, at 12 kilobytes. And we're also going to assume that the super block starts at 0. We're also going to assume that the inode bitmap is at address 4 kilobytes. So the IMAP bitmap here is at 4 kilobytes. The data bitmap is 8 kilobytes. And we're going to assume that the inode table comes directly after. And these are very general assumptions to make. These are in general how these things are set up. Okay, the sizes might vary, but this organization of super, then IB map, then DB map, then inode table is in general how it works. Okay, so to read the inode number 32, the file system would first calculate the offset into the inode region. So to calculate that offset, we take 32, which is the number, and we multiply it by the size of the inode. Okay, and that is simply 256 bytes. Okay, and that gives us 8,192. We then add it to the start of the address of the inode table on the disk. Okay, and that start address was what we said, 12 kilobytes. So we add the start address of the inode table to that offset. And that offset was basically 8 kilobytes. So we get 12 plus 8, and that's equal to 20. So the inode number 32 is at 20 kilobytes on our disk. And just by simply like visually looking, that makes sense, right? This block here, I block 2, starts at 20, and here's 32. So that's how you can calculate where the inode is on the disk. So what is actually stored inside of the inode? Well, it has all the information about the file. So it has the file type, the size, the number of blocks allocated to it, the protection information, the time information, everything, all the metadata related to that file, as well as the inode number, of course. So it's virtually all the information about the file. Okay, so that's the inode. Now, to support bigger files, we basically take this idea of the inode a little bit further. And that is through the use of a multi-level index. Okay. So system designers or file system designers have had to introduce different structures within inodes themselves. Now, one common idea is to have a special pointer known as an indirect pointer. So instead of pointing to a block of data, a block that contains user data, it points to a block that contains more pointers. Okay, so in general, the idea here is that an inode points us to a block that stores data pertaining to a specific file. Okay, but what if we just had an inode that points to another pointer that points to a block of data? This means that an inode may have some fixed number of direct pointers which points directly to data, okay, like the example here. All right, we have inode numbers pointing directly to data, and it might have one additional indirect pointer if a file grows large enough, and this indirect block will be allocated to this indirect pointer. And it will be allocated from the data block region on the disk, right? And the inode slot for an indirect pointer is set to point to it. So assuming you have 4 kilobyte blocks and 4 byte disk addresses, that basically adds another 1024 pointers. So the file now can grow to be 12 times 124 times 4K. In other words, around about 4,000 kilobytes. So what do I mean by this? What does it look like? Well, the idea here is that, well, you would say 0 to 11, all pointed to just data blocks, right? That would be this 12 value here, okay? And then what if we said that, well, we had an additional indirect pointer that points to a block which contains pointers to even more blocks? So here we can see how we get the 1024. We take the block size and divide it by the address size, which was 4, and the block size was 4K, which gives us 124. And now this block is basically made up of 32 by 32 entries, right? Which is the square root of 1024. So we have a 32 by 32 block, which each value in this block is now pointing to other data blocks. So we just simply add them together and times by 4, because that is the size of a single block. Okay, but we can take this even further. So not surprising in such approach, you might want to support even larger files. Now to do so, you just add another pointer to the inode, and this is called a double indirect pointer. Now this pointer refers to a block that contains pointers to another indirect block, each of which contains pointers to data blocks. So I know this is getting a little bit convoluted, but how it works can be described by this diagram here. So say we have a indirect pointer or an indirect inode value. This points to a block, which points to like I demonstrated originally. Or we can have a double indirect pointer, which points to a block, and each of the elements in this block points to another block, and each of those elements point to data blocks themselves, to actual data blocks. So you can see how this scales out by a factor of 1024, essentially. So that's how we get 12 plus 1024 plus 1024 squared, because this is the squared component coming in here. So with this structure, you can see how we can get to files that are quite large, right? So assuming that the block size is 4 kilobytes and you have 4 byte pointers, this structure can actually accommodate a file just over 4 gigs in size now. And the last case is, well, you can get a triple indirect pointer where, well, this block points to another block, and each of these elements in this block point to other blocks, which points to data blocks, and it gets quite deep. Okay, so that's how we can extend the idea of that's how we can store larger files. So just in general, the idea here is that these inode values basically point to data blocks, which has the file, the actual file. Okay, so let's look at the other side of the wheel, right? We've looked at files. Let's look at directories in a bit more detail. And directories have a simple organization as well. A directory is basically just a simple list of entry name and inode number pairs. And for each directory in a given directory, there is a string and a number in the data block or blocks of the directory. Now for each string, there may also be a length, okay, assuming if there's variable size names. So let me just explain this a little bit better with an example, as you can see here. So for example, let's assume a directory called dir has an inode number of 5. Okay, so that's that one there. I just don't want to allude to that too much. And it has 3 files within it, okay, foobar and foobar. And each of these have an inode of 12, 13, and 24 respectively. And the on-disk data for dir might look like this, basically. Okay, so here's foobar and foobar, and you can see the inode numbers, as well as some other information. So in this example, obviously each entry has an inode number. Now this is a record length, which is the total number of bytes for the name plus any leftover space. Okay, so things with longer names obviously will have a longer record length. A string length, which is the actual length of the name. Okay, so this is the specific actual length of the name. All right, and note that each directory also has 2 extra entries. The one is simply dot, and the other one is dot dot. Okay. Now dot is used to indicate the current directory, and that's why you can see the I number 5 is corresponding to that. And dot dot is used to indicate the parent, okay, the parent directory. Now, you might be wondering where exactly directories are stored. Well, directories is basically just a special type of file or another type of file, right? Thus, a directory has its own inode, like you can see there with 5, with the value 5. And this is stored somewhere in the inode table. And the directory also has data blocks pointed to by the inode number, and these data blocks live somewhere in the data block region of our simple file system. So our on-disk structure remains basically unchanged. So this structure up here, if I go back a couple slides, when incorporating directories, this structure remains unchanged, right? You'll have your inodes that point to data regions, and whether it's a file or a directory, it works in the same way. Okay, so let's think about actually accessing or reading a file from disk and how this affects our, or how this process looks if we had to traverse it. So say we had to issue an open, right? Or we wanted to open this file. This is the string of events that would occur, okay? I'm not going to go into too much detail. You can read through it if you want to. But after you do the open command, well, then you would actually have to read it. Okay, so once the file is open, you can then read it, after which you'll then close the file. Okay, so instead of reading through this, I want to actually go through this example in this type of format with this trace. So what we're doing here is basically tracing the reads or tracing the process of reading a file from a disk. So in this example, let's just assume that you want to simply open the file called foobar. Well, sorry, open the file in the directory of, open the file called bar, and it's found in the directory foo. Okay, we're going to read it and then close it. And for this simple example, we're going to assume that the file is just 12 kilobytes in size. In other words, just 3 blocks. Okay. Now, when you issue the open or the open command, which is like that open and then foobar, what ends up happening is that the file system needs to find the inode for the file bar. Now, to obtain some basic information about the file, so it does this to obtain some basic information about the file. So to do so, the file system must be able to find the inode firstly, and with the inode, it can then obtain the information regarding the file that we want. But all it has right now is the full path name. Okay, all it has is the foobar component. So it must be able to find the file, or find the inode, sorry, with that information. So what the file system does is it traverses the path name and thus locates the desired inode. Okay. So all traversals begin at the root of the file system. So at that slash, remember? And that is our root directory, which is simply called by that slash. So thus the first thing that the file system will read from the disk is the inode of the root directory. So that's what you can see here. The root inode is the first thing that gets read. Okay. But to find this root inode, we need to know to find this inode, we need to know its I number. So usually we find the I number of a file or directory in its parent directory, but root has no parent, and this is obviously by definition, right? So thus the root inode number must be like a well-known value, or like a constant value that is known, or like a global variable if you want to think of it in that sense. So the file system must know what it is when the file system is mounted. So in most Unix file systems, the root inode is 2, or the number 2. And this would be stored in like that super block. Okay. Thus, to begin the process, the file system reads in the block that contains the inode number 2. Okay, so the root inode. And once this inode is read in, the file system can then look inside of it to find the pointers to data blocks which contain the contents of the root directory. So it looks inside the root inode for the root data. Okay. So once it's over here, the file system will use these on-disk pointers to read through the root, the data components of the root directory. And in this case, it will be looking for the entry for foo. by reading in one or more directory data blocks. So it will, continue reading through the data blocks until it finds the entry for foo. When it finds the entry for foo, the file system will also have found the inode number for foo. Hypothetically, like let's say 44. And it will need this in the next step, right? So once it's found that, it can then read the inode number of foo. So the next step is to recursively traverse through the path name until the desired inode is found. In this example, the file system reads the block containing the inode of foo, and then its directory data. So it reads this block, finds the data over here, okay, which is the data block pointed to by the inode of foo, and in this block it will like traverse through it again, and it will find the inode number of bar. Now the final step after reading through that is to open or to read bar's inode into memory. The file system then does a final permissions check, which allocates a file descriptor. And if you remember back earlier, it would be when you're opening, it would be that file descriptor. And it allocates a file descriptor for this process in the per process open file table. And it returns that to the user. Okay. So that's the opening component, right? You go from the root to like the subfolder into the actual file by accessing the inode. Then the data will tell you this inode will tell you that data, and then this data will tell you finally the inode that we're looking for. Okay, and once we get there, we can actually open the file. Well, now that it is open, so once open, the program can issue the read system call to read from the file. So the first read will thus read in the first block of the file. So this first read will read in the first, this first read here will read in the first block of the actual file. Okay. And that is as a result of the inode that we found over here. The read will then update the in-memory open file table, so the file table of the specific process for this file descriptor, to shift it, to offset it to the next block, so that when we read in again, it's actually on the next block. And this process obviously repeats itself recursively until you've read all the data in the file. Now, at some point, the file will be closed. Okay. Now, there is much less work to be done here. So clearly, all that needs to be done is simply that the file descriptor should be deallocated. And that is all we simply have to do, is deallocate that file descriptor. Okay, so the next question would be then, well, what's the process for writing to disk? So in order to write, we have to obviously issue the write system call to update the file with the new contents. Now, this file may require the allocation of a new block unless you are overwriting a pre-existing block. And what this process also requires is the updation or the updating of the data block as well as the data bitmap. Okay, because remember the bitmap tells us what blocks are free and empty. So obviously we're writing to a new block. We need to adjust that or change that. What's interesting, the write call also generates 5 input-output processes. The first being one to read the data bitmap to see which blocks are empty and which blocks are full. One to write the bitmap to reflect its new state. So because we write into a new block, we have to change that block to be used. And 2 more to read and then write to the inode, updating the inode to point to that new block. And 1 writes to the actual block itself to store whatever information. So you can see this over here. So the creation of the file once again requires us to to traverse all the way to the specific file. And what ends up happening here is that we realize there is no file called bar inside foo because we traversed the whole thing and there's no bar. So what that means is we have to update the inode bitmap to indicate that we want to write to a new inode block. So that's what ends up happening here. We update our bitmap, and then we actually write to the new inode. Okay. And that's in general the process of creating. Okay. We also update our foo with this like new change now to indicate that, well, inside foo data there is actually that bar file, or you can find that bar file, or you can find the bar inode within foo data. So after that whole creation process, we can actually do like the writing, and here you can see those 5 input-output operations that we mentioned over here. So first we obviously read in the inode of the file, and then we update our data bitmap, or we first read which blocks are available and which blocks are empty, and then we write to it to update that. And then we actually do the write to the data, and then we write to our inode number, indicating that we're pointing to this patch of data. And then this process happens 2 more times, and that's basically the 3 different writes that we perform. Now you might be asking, well, how does it do this efficiently, or how can a file system accomplish any of this with any reasonable efficiency? Well, for that it utilizes caching and buffering. Now reading and writing files are expensive, and like you can see, they incur many input-output operations. And for example, for like a long path name, you can see how there would be multiple inode and directory references and operations that need to be formed to read like one packet of data, or one part of your data. And that would literally be hundreds of reads just to open a single file. Now, in order to reduce this I/O traffic, file systems aggressively use DRAM, or your memory, to cache this information. So each file system uses a fixed size cache to hold popular blocks. Just like we saw how our TLB is used to store popular pages, it's exactly the same process here. You remember we also referred to our TLB as like a cache. It's also used here to store popular blocks. Obviously not the same thing, the TLB isn't, but another region of our memory now is used to store popular blocks. And this is obviously a huge efficiency boost because it's a lot faster, because our memory is a lot faster than our storage devices. And since it's already in the memory, we can skip, just like we skipped in our TLB, that whole extra step of going along the chain to read the block into memory. So caching handles the reading, right? But what about the writing? Well, write traffic has to go to the disk for persistence to be a fact, right? Thus, the cache does not reduce the number of write input outputs, right? Now, therefore, file systems use write buffering to increase the write performance benefits. So what this means is they delay like writes to the file system and do it in like a batch. So instead of writing individual chunks of information, they group them in order to perform a single write operation that is obviously a lot more efficient, right? By buffering the number of writes in memory, the file system can then schedule subsequent input outputs and therefore reduce the number of write requests. So this has been our little introduction to file systems and like their implementation. In the last week, which will be our last week of lectures, we will do 2 more implementations, or 2 different types of implementations for file systems that are a little bit more complicated, but basically take this idea and take it a little bit forward. So thank you for listening. And once again, any questions, post them. to the middle page and I'll be happy to answer them.